is called uniform circular motion. And basically what this means is we assume that an object travels in a perfect circular path, or on a perfect circular path, at a constant speed. Let's see, I'm going to have to switch planes. Okay, so what does this mean? I'm just going to draw a nice picture for you. I've got this protractor over there. So if I just draw a part of this circular path, let's first choose a point of origin over here. So this is going to be our reference frame. And what we basically mean is we've got a circular trajectory like so. And we've got a particle that is moving all along this circular path with a constant speed. So let's look at two specific points. So let's say we look at when the particle is over there and when the particle is over there. So at some initial time ta, the particle is there. At some later time, it's over there. Now, would you agree with me that I can describe its position with respect to the origin by this vector? So initially, the particle is over there, right? So that arrow just gives me its position at that time. And here, that just gives me its position at some later time. Now, what will its displacement be between these two times? One subtracted from the other. So remember, our change in position is always final position minus initial position. So that means our change in position is that. Now, what will the velocity, remember we said the speed of the particle is constant, so this particle is moving round and round in a circle. What will its velocity be at that time? What direction will it point? Tangential. So, would you agree with me that the velocity will look something like this? Okay, its magnitude we haven't specified yet. Doesn't matter for this example. But at that instant, its velocity is pointing tangential to the track, and that just means that angle is 90 degrees. And by the same reasoning, we can say that over here, we've got the final velocity at some later time. So the velocity changes direction with time. Let's try to figure out just by how much. So I'm going to let's use our displacement just to have as a reference line. So I can use my protractor to measure that angle between the change in position and the velocity, and it turns out to be just 30 degrees. So if I take that velocity vector and I draw it over here, below, it looks something like that. And if I measure the angle between my displacement and my final velocity, I can see on the protractor that's also about 30 degrees. So I can draw my final velocity in over here, like so. And remember, they have to be of the same magnitude, because we assume circular motion implies the speed does not change, so the velocity's magnitude must remain the same. And if I want to ask you what was the change in velocity, we just again complete this triangle by saying, well, that over there gives me the change in velocity between these two times, because the velocity vector changes from being in that direction to being in that direction. So this means people have an acceleration. Acceleration is always the change in velocity over the change in time. And what I want to conclude with, so I know we're running out of time, is I want to show you that one can use this triangle and that triangle to actually figure out what the acceleration is in terms of the speed and the radius of the path. So what I'm going to do is I'm going to cut out this triangle physically, my scissors. And what you should see is that this velocity triangle now fits in perfectly over there. Can you see? It's like a smaller version of the triangle formed by my position vectors and the change in position. And the ratios of these sides, remember that side was V initial, that side was V final, that side was the change in velocity. I can now write, for example, if I take the ratio of the initial velocity over the initial position, so those magnitudes, it is, for example, equals to the ratio of the change in velocity over the change in position. And we're going to use this relation tomorrow to derive an expression for the acceleration. Thank you.